Okay, let's do a fun Gauss's law problem and one that's a little bit different. So, Gauss's law, right here, gives a relationship between the electric field flux through some closed surface and the total charge inside that surface. And normally we in introductory physics do this for simple situations that the integral becomes trivial. And let me start off with the trivial case just so you can see how trivial it is. Suppose, and here I'm going to verify it actually. So here I have the electric field due to a point charge. So the electric field due to a point charge, if the charge is at the origin, r is the vector from the charge to the place that we want to find the electric field. So r hat would be in the same direction, and so you get the electric field E like that. The electric field points radially away from that charge as a positive charge. Now suppose I want to calculate the flux. This is a spherical surface, and a sphere is super easy because flux is this surface integral of E dot n hat dA. So I have to take the electric field E, I have that. N hat is a unit vector pointing away from the surface. It's perpendicular to the surface. So at this point, n hat is that same direction. So if I break this into a little piece, dA, then E is in the same direction as n hat. So no matter what they are, E dot n hat is just going to be E. Okay, the magnitude of the electric field. And then I can just multiply, and it's constant, right? As I go around the surface, since it's all the same distance away, r doesn't change, so the magnitude of E is constant. So in fact, this becomes the integral of E dot n hat dA becomes the integral of E times dA. I can pull the E out as a constant. If I pull it out, then I have the surface integral of the surface, and it's just a sphere. So the integral of the surface area of the sphere is just 4 pi r squared. So it's going to be E times 4 pi r squared. And then if I put in my value for E right here, I get 1 over 4 pi epsilon naught q over r squared. I don't have that r hat, so I have the magnitude, equals q over epsilon naught. Oh, yeah, so that. Well, I forgot the 4 pi. So then I have this other part, 4 pi r squared. The 4 pi's cancel, the r's cancel. I get q over epsilon naught on both sides of the equation. Done. So, and really a lot of times we use Gauss' law to find the electric field. I'm just showing that it works in this case. And that's a trivial case. It's not even hard to do. But what if I put, this says the flux through any closed surface is equal to the charge n divided by epsilon naught. So what if I put it in the middle of a cube? And so I want to do this as a cube of length a on all the sides. And so I want to calculate the flux through this whole cube and show that the flux through this cube is also q over epsilon naught using this electric field. Of course, it's not trivial. Let's just imagine what's going on here, though. I have here the electric field on the surface is this way, over here, on the back side's that way, on this side this way. It's pointing away, but it's not constant over that surface. Over in this corner, it's actually not even in constant direction. It's pointing at that angle. But what is constant, if I have the cube centered on the origin and the charge at the origin, I can actually break this into 6 fluxes, 1 flux for each side. So the magnitude of the flux for all 6 sides should be the same because it's symmetrical. So I only have to calculate the flux through one side and then multiply by 6, and that should give me my answer. Okay, so it's not too easy. I'm going to call this the x direction, y direction, and then this will be the z direction. So let's look at this plane right here. I'm going to draw it from the side, and we're going to calculate the flux, and it's going to be awesome. And you're going to have a good time, and I'm going to have a good time too. And don't make me make you have a good time, because you're going to have a good time. Okay, and you'll see why we would not normally do this, but we will here because it's fun. Okay, so here is my axis. Here's my y. There's my x. There's my charge. And then so I'm going to have, and just to make things easier, I'm going to have a box of, it doesn't matter how big the box is. So I'm going to make it 1 by 1 by 1, just so it's the easiest unit. So here's my box. And so this is the x-axis, and this is the y-axis. So this is in the yz plane. This goes from negative 1/2 to 1/2 in both the y and the z direction. And then this is at x equals 1/2, right? Because that's this x is 1/2. There's another one on the other side at x equals negative 1/2. So let's pick a little piece right here, and I need to find the flux right there. Now, you may think, okay, we could do this in spherical coordinates, we could do it in polar coordinates, we could do whatever, but the surface is in Cartesian coordinates, right? So I'm going to use Cartesian coordinates. I need to do two things. First is, the nice thing about this problem is n hat is constant. I can actually write n hat as the vector 1, 0, 0. The unit vector for the surface is flat. So n hat is just the x direction, which I write as the vector 1, 0, 0. Now I need to find this, r. Because remember, I'm trying to do r dot n hat, and then I can integrate over this surface, which is in the yz plane. So I can just write the vector r. Since the charge is at the origin, I can write this as r equals vector x, y, z. So it has an x coordinate, it has a y coordinate, it has a z coordinate. Simple. Not simple, I'd take that back. So I'm going to write the electric field as a vector. I can't just write it as a scalar. 1 over 4 pi epsilon naught q over the magnitude of r squared times r hat. But r hat is a unit vector in the direction of r. So I can actually say r hat is the vector r divided by the magnitude of r. That's how we define that. And if I do that and put that in, I can actually rewrite this in maybe a more useful form. E equals 1 over 4 pi epsilon naught q over r magnitude cubed times the vector r. So hopefully you can see that these two are the same thing. Now what about the magnitude of r? Well, if that's my vector r, the magnitude of r is just going to be the square root of x squared plus y squared plus z squared. So now I can write this as a vector. E equals 1 over 4 pi epsilon naught q over the square root. No, I'm going to put it like this. Let's say E equals 1 over 4 pi epsilon naught q over x squared plus y squared plus z squared and to the square root, but then I have to cube it. So it's going to be to the 2/3, the 3/2 power. I'm sorry. The 3/2 power. And then I still have r, which is the vector x, y, z. Because that's all a scalar value. So I don't have to worry about writing that. So this is my scalar component, and then multiply by that, and I get my vector. Okay, so now I know n hat. So I remember I'm trying to do this. I'm trying to do the I'll say phi 1 is a surface integral. It's a double integral from y equals negative 1/2 to y equals 1/2. Z equals, I'm going to draw a picture of this in a second. Z equals 1/2 negative to z equals 1/2 of this E dot n hat dy dz. So my area element in this plane is since it's in the yz plane, is dy dz. So let me just draw a little, if I draw this as an angle picture, here's my, so this is this. So this is my little piece right here. So this is actually this is the z direction, and that's the y direction. So this is dy, what's dy is the vertical one, dy, and that's dz. So the area of that, and the unit vector is in the x direction. So if I take E dot n hat, so I can say that's just going to be, I have to take the dot product of this and that. But that means 1 times x plus 0 times y plus 0 times z. So E dot n hat is going to be this. 1 over 4 pi epsilon naught, that's a pi, q over this x squared plus y squared plus z squared to the 3/2, and that's just going to be x. And then that's that. It's just because I took the dot product to get a scalar. So now I can put this in up here, and I have the following integral. I'll just put this as phi 1 equals, let's just call that y z 1 over 4 pi epsilon naught q over x squared plus y squared plus z squared to the 3 halves x dy dz. So I have to do a double integral. I have to integrate over y and I have to integrate over z. But I have actually, I need to simplify something, right? Because x is a certain value. On all over this surface, x is equal to 1/2. So that's nice. And also have some constants. So let's pull those constants out front and rewrite this in the simplest form before we do the double integral. Okay, so let me put that right there. So let's say I have phi 1 equals, I'm going to pull all the constants out front. I had that 1/2, so I actually have 1 over 8 pi epsilon naught. And I don't have another, and q, I'm going to pull the q out too. Q. Yeah, and then I have the double integral, the z, the y, 1 over 1, I'm pointing at that, you can't see it. It's x is 1/2, so it's 1/2 squared, so I get 1/4, plus y squared, that's a 4, plus z squared, that's a plus, to the 3 halves, dy dz. So that's what I need to integrate. In theory, it's not that bad, right? Because I can integrate over y, because this is going from negative 1/2 to 1/2, and I can treat the z as a constant, and then I can do it again for the z. This integral is not, if I do that first integral, I think I found it in this integral table. So here I have the integral of dx over a x squared plus c m to the m plus 1/2. So in this case, I'd have m equals 1. And then so I could write it this way as x over the square root of ax squared plus c. And then this is r is 0 to 0. So I think I'm not sure. I don't really want to do the integral. I'm actually going to do this integral, but I'm going to do it 2 ways. The first way, once you getting to this is a big deal. Okay, don't think, oh, you're only halfway done. That's true, I get it, but it's still just an integral. If you could look this up in the integral table, even if I did this first integral and then evaluated that and do the second integral, it's going to be a little messy, right? I got to evaluate that, the limits, and then do another integral. It's a little messy. So let's just go ahead and use an online tool, and then I'm going to do it numerically in Python from scratch because I think that's awesome. So I'll do it 2 ways. Okay, so let's switch over here to Python. No, we're not using Python. I'm going to use this in a second. This is WolframAlpha. I found this, and I'll include link this down below. This is a double integral calculator. Isn't that nice? And so they want the function in terms of x and y, and then the dA element, and then the limits of integration, and I can just do it all from right there. Okay, so my function, I just need to enter this in. Is this big enough? Can I make this bigger? What if I do this? One more. Okay. There, you can see that now. So WolframAlpha, I'm really pleased with. You don't even have to have an account to get a lot of great stuff out of it. There are other ways to solve this. There are other symbolic integral calculators, as you will. But let's just go ahead and enter this in. So f of x, y, I'm going to enter this as, I'm going to raise it to the negative, I'm going to have the function to the negative 3/2 power. I think I'm going to do it that way. So I'm going to say 1/4, so let's just put 0.25 plus y squared, and I think this case you can just write it like that, plus z squared, all of that raised to the negative 3/2. That's it. I'm doing dy dx. I'm doing from x is negative 0.5. Let's say negative 1/2. Let's do 1/2. Negative 1/2. Let's see what happens. To 1/2, and y from negative 1/2 to 1/2. Okay, let's see if that works. Something's happening. Kind of excited. Okay, computing. Input. That looks right. It didn't give me the answer though. Input. Maybe it's still working on it. dy dx, negative 1/2, 1/2. I'm pretty happy with that. Let's see, it does not just maybe my screen's too big. Submit. I submitted it. Input. I thought I did this before and it worked. Submit. Computing. Oh, I know why, because I did y and z instead of y and x. So I need to change this to x. Sorry. Okay, there he goes. So this is my answer. This is important. 4 pi over 3. So let's switch back over there and see that this works. Let's switch back to the paper. Okay, so here I am. I'm just going to say this is equal to, I still have my other stuff out here. I still have q over 8 pi epsilon naught, and then I get 4 pi over 3. So the pi's cancel. This cancels, makes that 2, and I get q over 6 epsilon naught. Now, if I do the other functions, so I do, this is the total flux is going to be 6 times the flux through 1. Then I get q over epsilon naught. And, you know, sometimes I'm even amazed that it even works at all. But it did indeed work. Hoorah for us. So the flux through the cube is the same as the flux through the sphere because they have the same charge inside. Okay, now let's do this in Python. So in Python, we want to do a double integral, and I want to do it numerically. So the difference here is, suppose I have this square, and this goes from, let's call this the y, and call that the z direction. So this is from negative 1/2 to 1/2, and this is from negative 1/2 to 1/2. So what I'm going to do is I can calculate anywhere on this surface. I can calculate a function f of x, actually this is going to be f of yz, right? It has every location in here has a y and z value, and then I have a function right there where f of yz is equal to 1/4 y squared plus z squared to the negative 3/2. I have that function. So what I want to do is I need to multiply it by my area element and then just go through and add up all the elements. So if I start right here and I pick a little square that it has a width of d, it's dz by dy, and I have actual sizes for those. So let's say it's 0.1. I can calculate the flux through that piece right there because I assume that function's constant over that whole tiny little square. And then I just keep doing that from y equals, that's z, from z equals negative 1/2 and just do it all the way up here to that. And then I repeat that, I move over here and I do it this way. And then I move over here and I do it this way. Okay, so that's what we're going to do in Python. We're going to break these into tiny little squares and we're going to add up the total area, or the function times that element area over that whole thing. So we have to do a double loop in Python. Okay, let's do it. Okay, so here is, I gotta switch. Computer. So I'm switching over to Python. I'm gonna give you the code for this. I'm using GlowScript vPython, and there was an error in here. I tried something earlier. This uses Python 3.1, which gives me an error, so I switched to 3, and it works fine. The first thing I want to do is to make a function for my function so that I can call that. So let's make a Python function. I'll say def f of, I need to give it a y value and a z value. I'm going to call this yt for temporary y and zt for temporary z. And now I'm just going to return the function just so I don't have to keep typing it. And it's just like I said, it's going to be the function, I can put parentheses, 1/4, which is 0.25, plus yt squared, plus zt squared, all of that raised to the negative 3/2 power. That's right, 3/2? Yep. Okay, so let's just test that. I always like to test that. So print f of 1, 2. Let's just see what happens. You never know if you have a typo or something like that. -6. Okay, that seems right. Okay, now I need to pick my actual size of my elements. So I'm going to say dy equals 0.1, dz equals 0.1. So now if I go from -1/2 to 1/2, that will be 10 steps. And I like to start with something big in case there's an error. I don't make the problem worse. We can always make it smaller later. That's what's nice about Python. Okay, so now I want to start with y. I want to start in that corner. So I'm going to say y equals -0.5. Y equals -1/2. I also need to say z equals -0.5. I have to start with values. Now, the one other thing I need is the total flux. I'm going to calculate the flux through each box, move up, move up, move up, and then repeat that for the next value in the y direction. Well, I'm actually going to do y and then z. It doesn't really matter which one you do first. But I need to have some function to add my pieces too. So I need to have like a total counter. And that's going to be, I'm going to call it phi equals 0. So I can add something to that. So now let's make the loop for z first. Actually, let's do y first. So if the while loop for y looks like this. While y is less than 0.5, do the following. And the first thing is to just calculate the function times dx times dy dz. So I'm going to say d phi is f of yz times dy times dz. I mean, it's as simple as that. That's the integral. Now I'm going to add that to my total. Phi equals phi plus d phi. And then I'm going to increase my y value. Y equals y plus dy. So this will not do the whole thing. This will just do one loop of y. And let's just see if it's working. I'm just going to print phi. Let's just see if it works. Okay, so it gave me a number. I don't know if that's the right number or not. It gave me a number though. Let's save this. Double integral. I don't know. Okay, so but now I want to redo that whole thing a whole bunch of times moving in the z direction. So let's say this. While z is less than 0.5, I want to do all of this stuff. So I'm going to highlight all of that stuff and indent it. Now it's part of that loop. It's going to repeat it. But at the beginning of each loop, if you imagine I'm adding up in the y direction, once I go to the next thing, I got to go back down to the bottom. So I got to go here and say y equals -0.5. Otherwise, that second loop wouldn't work at all. And then down here at the end of this loop, after I finish the y loop, I need to increment z. Z equals z plus dz. That's it. I think that's it. So let's do that. Print phi, run it. -1. Okay, something wrong happened. Oh, I know what I did wrong. Star. Okay, 4.168. Remember before I had 4.188. But this is with a 1/10 of a step size. So I can make that smaller. We can make it, doesn't cost me anything to make this smaller. That's pretty good. I can make it even smaller though, because I can just want to show off, right? 0, 0. It takes a lot longer. Okay, so 4.118. 4.188. Let's just print this just to see if it is the same. Print, what was it, 4/3 pi? 4 times pi divided by 3. And let's see if we get the same thing. That's like the same. Okay. So this numerical integral is one way to do that. Now, you do have to have actual limits of integration, but now I can put that same number in and multiply by my other values that I had, which was 1/8 pi. And if I divide that by 8, let's just do that. Let's just divide this. Divide by 8 times pi. And I get 1. That's 1/6. So it won. I won. We all win. Everyone wins. Okay, so I'm going to give you a link to, if you want a link about Gauss's law, I have that. But I am going to put the link to this code down below. I'll put a link to the WolframAlpha double integral down below too. And I hope you find that useful.